For this review video, I'm going to roll two topics into one. There was probably a even split in the topic that won second prize for most confusing from last week's lecture, and that was the design of the reverse primer and the confirmation of an integration event, of a tDNA integration event by PCR. So let's just do the regular primer design first, because it's the earlier in the unit. Just give us one more round of practice with that. So I'm going to call up here a image of just a random DNA sequence, so we can use that as our guide, I suppose, or as our target sequence, and that should be right there. And let's say that we want to, you can see the ATG there in red, that's the start codon presumably, and then it looks like we go all the way to the stop codon italicized. So as I look at this, I see the last codon is a TAA or UAA and the RNA, and that is a stop codon. So it looks like the open reading frame is here in all of italics. So let's say we want to amplify a DNA fragment, a PCR product, that encodes or captures or amplifies all of the coding region, everything that's in italics. So you know the rules pretty well. I can tell in the reflections that you got the rules decently about melting temperatures and GC content. But I'm just looking at the top strand here. This is not double-stranded DNA. This is a single strand, the top strand listed for us. So I'm just going to scan here quickly to see if I can find any non-repetitive sequences that seem to be about 50% GC. This looks like it might be a decent one here. Maybe a little heavy on the T's and the A's, but let me do that. So that's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. Not too bad. Probably what I would do here, because I didn't prepare this ahead of time, I would probably steal some C's and G's from earlier on that are non-repetitive, get me closer to 25. So that looks like a pretty good forward primer to me, and I would just copy that primer down as it is written. So my forward primer would be, in this case, C, G, C, C, G, T, A, G, G, A, C, A, C, T, T, G, A, T, T, A, C, G, A. And I'm just going to quickly count up my C's and G's. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and about a 25 nucleotide primer. So that's good. I like that one. Doesn't look repetitive. It's got about 50% GC. It's going to have a nice melting temperature. So that's what I'm going to run with. Copied right off of the top strand. It will anneal to the bottom strand. It's going 5' to 3', truly left to right. That means the 3' end would be here, pointing inward. We are golden. Now if I do the same thing, but I look at the later period of what we want to amplify, again I'm looking for G's and C's, fairly not repetitive, something that's going to give us a pretty good mix. This looks decent here. That's going to be about 24 nucleotides long, and A's and G's, let me see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 out of the 24 are C's and G's. It's a little bit on the heavy side, but there's not really an opportunity to pick up many more A's and T's nearby without making the primer too long, so I'd probably stay with that, even though it's a little heavy on the GC content. But all of that said, knowing that this is the reverse complement, this is the reverse primer, I need to think a little bit more about this. So this primer needs to be the complement of the sequence that I have circled in purple, and it needs to be written backwards. So as I've recommended to you guys in class, I would first write the base pairing here below this target sequence, get the base pairs written in, and then recopy that sequence right to left rather than left to right. I'm going to do it in my head just because I've designed a lot of primers and I want to save time on this portion of the video. The reverse primer sequence here for this primer appropriately would be A, G, 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 C, C, G, C, A, C, A, T, G, C, G, A, C, 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 T, T. That would be the reverse primer sequence. You can see what I did, I hope. I took the complement of this sequence, but I wrote it down in reverse. This A would base pair with this T, this A with this T. 4 A's, 4 T's, followed by G, 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 C, C, G, C, A, C, A, T, G, C, G, A, C, 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 T, T. That's the reverse complement, and that's it. Those are two good primers. The top primer matches the top strand. The reverse primer is the reverse complement of the top strand. This reverse primer, as I've written it here, is going 5' to 3' written. These A's would anneal here. These T's would anneal here. And that means the 3' end is pointing inward towards the sequence that we're trying to amplify. Pretty good primers. So that's it for the primer design. Let's talk about DNA disruption. So again, I'll try to use the same symbols that we used in class. Let's imagine that we have a gene, and I'll represent that gene as an open rectangle. What I mean by that is that the ATG of the start codon is at the beginning of the rectangle, and the stop codon of that gene, whatever it might be, is at the back side of the rectangle. And we want to disrupt this gene. We want to insert some transforming target DNA right into the middle of this coding region so that it's completely disrupted. And we're going to do that with a targeting DNA or a transforming DNA cassette. Now, if we can get this purple disrupting DNA to embed itself into our gene of interest, we will have disruption. We'll have nullified the gene. In order to determine whether or not we've successfully done this, we're going to use a reverse primer that anneals to our tDNA, but the way that it anneals is that the 5' end is on the right and the 3' end is on the left. Again, it's a reverse primer, so we know that the orientation of amplification is going to be this way. And we also have a primer that anneals here in our target DNA, the gene that we want to disrupt. This is a forward primer, so it's going to go 5' to 3' left to right, meaning it's pointing towards an amplification in this direction. Now, as I've drawn this now, you can see that amplification is not possible because the two primers are not in close enough proximity. Also imagine that if that transforming DNA localized to some other chromosome or some other region, yeah, the reverse primer would anneal to it, but the forward primer is still up here. And because these primers are not within 8 kb of one another, they're not on the same piece of DNA in close proximity, we won't get a PCR product. But if and when our transforming DNA does embed itself and insert itself and disrupt our target gene of interest, now that reverse primer anneals in close proximity of the forward. It anneals in the proper orientation with its 3' end facing inward, and we will be able to amplify a DNA product that starts at the forward primer, continues to the reverse primer, one continuous piece of DNA in less than 8 kb of sequence amplified, and we will be able to generate this PCR product. The only way that this PCR product could ever have been amplified is if our forward primer and our reverse primer annealed on the same chromosome of DNA within 8 kb of each other. That means the only way that this PCR product could have been successfully created is if our transforming target DNA truly targeted into and disrupted our gene of interest. So that's that idea of a PCR application for verifying that correct disruption has occurred. It's all about proximity. It's all about knowing that one primer anneals to the tDNA, the other primer anneals to the target sequence that we're trying to disrupt, and the only way those primers can work together correctly within 8 kb of one another, pointing in the right direction to create a PCR product, the only way that we could ever get this PCR product is if that tDNA landed within, correctly targeted to, our gene of interest, and created that disruption. Any other questions, please let me know, but that's really all that we need to know about using PCR to verify targeted disruptions, and also hopefully a quick little primer on reverse primer design.